For anybody who does not know, David Mestre runs the planetarium at the Discovery Museum, and he flew in today just for us.
I know.
You got to tell us a little bit more about the planetarium.
Yeah, tell us about the new gizmo.
All digital goodness.
So it's for those who are not familiar, we did get actually some money in a bond to do an upgrade at the planetarium. You guys are all invited to come down to check it out. It's just been recently installed, probably since last October.
I've seen it.
It's about like $350,000 worth of projection equipment. So we took out the mechanical projector.
And you have to see Mario Kart on it.
Yeah, I know. So we took out the mechanical projector. It's now a piece of sculpture in the lobby, so we still preserve that. It's got the dual 4K projectors in north and south of the dome, and we're using a Evans and Sutherland Digistar 6 system, and it screams. It's incredible. It's got a rack of just 3 computers. It's got a host computer and 2 graphics computers that runs each of the projectors. Surround sound system, a 5.1 surround sound. And then some of the things that we've also added to make our facility a little more handicap accessible, we've actually got little headsets. So if you have hearing impairments, we've actually added that as well. So it's wireless headsets that go to our audiences that have a little, we're thinking about you. So we wanted to make sure that everybody feels like they can enjoy the show.
You also get big rapid updates too, right?
What's that?
Updates.
Oh yeah. So there are a couple of really cool things with this system. So anything that happens in the sky, typically I can get over there in the next morning, and content has already been added into our Digistar system. What's also very cool is that we're part of a community of Digistar users, and being part of this community is actually Digistar Cloud. And so other planetaria all around the world that use this Evans and Sutherland Digistar 6 system are able to actually add content to it as well. So we had somebody made a screaming video in 4K in immersive theater format of New Horizons hitting Ultima Thule within 3 days of the event, and added all the content into it and everything. There is actually a scripting language, and so it was.
Isn't that the stuff that Carter made? Down in
it's different. So what Carter has is what's called Open Universe, and so it's similar in terms of its. It has a language construct that allows you to actually control all the graphics and the content and all the data. Evans and Sutherland is more of a proprietary system. The Open Universe is an open source system, but it actually can operate in Argo too if we're thinking of doing that. We've just been kind of focusing most of our efforts on the Digistar 6 system, but the stars look really, really impressive. And so that was one of the things that I was really kind of worried about. But once they install the 4K projectors,
did you do anything inside differently too? Is it because it's always been a reasonably small, intimate room? Yeah. Is that changed at all?
No. So what we haven't changed the actual format of the seating arrangement. It's still sort of all unidirectional, but what we have thoughts are, there's a couple thoughts processes that we're going through. We're thinking maybe removing all the seats and putting removable seating, and so that we can actually have the entire space open and create different types of programming. So some of the educators came up with ideas where we could actually do a pretend campfire and actually put it in the dome and have kids going around there, little bean bags and that kind of stuff. So different ways of actually playing with the system.
You should wire the seat so when you go through a magnetic field, just
totally immersive experience. Right. So it's a lot of fun. So we do, if you guys want to come down, definitely around Space Day. I'll definitely sneak you guys inside and we could do something special this week.
What day is Space Day this year?
I think it's April. I got to check. That's a good question. So let me double check on that.
I mean, we come again. I just give some notice.
I'm gonna let you have that and some right over here.
All right. So incredible system. So we're really excited about that. And we may not be the only one that's going to have a 4K system. So it looks like Milford Foreign High School is thinking of getting one too. Oh, and they were debating a system to get for their planetarium. And once they saw our system, they said this is the system that we want. So we were pretty excited about that. So we're thinking we might be able to create a community of practice here in the state of Connecticut with all the different Digistar, Evans and Sutherland star systems. So, I want to kind of give you a little bit of an update. I gave a little talk a while ago about some of our high altitude ballooning, and our museum has partnered with a lot of different people, other universities, amateur radio clubs, some amateur volunteers, David, with some really interesting projects that serve as a platform to really teach and inspire kids to consider careers in engineering. So this is sort of a way for us to be able to do some science and some engineering, and also a little bit of inspiration as well. Now, why do we consider high altitude ballooning? One of the things that it can allow us to do is test hardware in near space environment, near space conditions. We can use this platform to interrogate the near space environment. So we can actually bring sensors up to these altitudes and actually interrogate that environment. It can simulate a space mission, at least the way that we've done a lot of our high altitude ballooning with mission planning and engineering design. We do launch, tracking, communications, descent, and recovery. So there's a lot of parts that go into a high altitude balloon mission, and we try to replicate what goes on in a real high altitude balloon mission with NASA when they actually do a lot of their high altitude balloon work, either out west or in Antarctica. So we're just kind of a little microcosm, a baby version of what they do down at NASA. And one of the things that is very important about this is that it is cheap, right, compared to any other kind of research related to doing space exploration, satellites, and that kind of stuff. High altitude ballooning is actually a very good place to actually do this kind of educational work because it's actually pretty cost effective and doesn't really need a whole lot of money unless you really want to spend money, which is sort of what we've been doing. We use high altitude ballooning at the Discovery Museum to really kind of inspire and engage students. And a lot of what we've been working on has been a lot of the technology development. So we've been doing a lot of research and development and trying to figure out how to do high altitude ballooning in a compelling way for young people. We're using a lot of museum assets and building some competencies to be able to create these near space mission experiences. And then we're also working with some public and private and volunteer partners in order for us to be able to solve a lot of the engineering problems that go into high altitude ballooning. The kicker is that we've got a lot of assets already at the museum that we're really trying to hook and put together to create sort of a little mini NASA at the museum. And what we have at the museum is it's a Challenger Center. It's a simulated space experience. It has two rooms, one room that looks like mission control and the other room that looks like a spacecraft. And so we've been doing simulated space missions at the Discovery Museum since around 1991. And we're part of a network of Challenger Centers all across the United States. And there are actually about 2 or 3 foreign Challenger Centers as well. The big idea is that we wanted to turn this mission control or mission operations center into a real, fully functional mission operations center, where we weren't just simulating missions, we were actually doing real missions. And so to do that, we needed 2 extra parts. One, we needed communication to assets in these extreme environments, whether balloons or satellites. And so a number of years ago, some volunteers and a very generous donation from one of our stakeholders got us a satellite tracking antennas to mount up on the roof.
He's one of our generous donors.
He's dead. Dave Ives! So Dave Ives has been a real incredible support for us. And we're still using the system, and this system has been the linchpin for any of the ballooning that we do, because this allows us to do something that practically no other balloon can really do. If you wanted to do ballooning, you can put your GoPro on a balloon and let it fly and hope you can find it again. Our system has been able to do tracking, telemetry, and communication to the balloon and receive information from the balloon. So we've got the steerable antenna, and this allows us to track our hardware. And then the key thing is the actual hardware itself that we put into the extreme environment. And so, so the idea is to put all these pieces together, a mission control, the communication system to be able to talk to the hardware that's in the extreme environments, and to develop the instrumentation and hardware for these payloads to be able to provide a compelling experience and a telepresence so that students that are in mission control are actually running a space mission. And so that's sort of like the more than a 30-second argument or a 30-second elevator speech or something like that. That's basically what we're trying to do. In short, I try to encapsulate it into a little statement that what we're trying to do is a space program for kids. It's turned into a space program for adults that really think like kids, and that's basically what's going to happen. But we're gonna try and sneak in the students in there. But what we've been really working on is a lot of the research and development and the technology to be able to do this. So that's been pretty exciting. One of the probably our moment that really put us in the high altitude ballooning map was our first balloon mission with members of WAS. And so those guys were here, and that was hard to believe. That was actually about it's going to be pushing 5 years since we actually had that mission. We had a number of partners that helped us on that mission, and we were able to launch this high altitude balloon. And now it's was that yeah?
Horribly smell.
Did I spell your name wrong? I know. It happens.
The Q is silent.
Is it really? Okay.
There's no Y or K.
Oh my God! Doesn't have a Y or a K? Oh my God! I know. Seriously, this has gotten all the mileage. I'm sorry. All right, good. All right, I can change it. I can do that.
Might be easier to change your name at this point.
Yeah, exactly. Yeah. Sorry, Dan. This was okay. Anyway, so a couple of things that we did was we do a lot of student training, and so during that first mission, we were able to actually turn it into a giant fox hunt, and we actually taught the students how to actually find the hardware, and the hardware turned out to be Larry in his Subaru running around all over Shelton. And once he hit a little box, we went with our GPSs trying to find what would be the balloon. So this allowed us to actually learn a little bit about how we would actually do ground operations and ground recovery operations. So that was pretty exciting. For launch operations, you can see right here the amount of people and the hardware that we need to actually just launch this first mission. Here's our launch. This was our crowning moment right here. And you can see Larry, he's one of our engineers, and a number of our University of Bridgeport partner students. And our mission was to actually launch from Bridgeport, go up to about 30,000 feet, and we had a mechanism to be able to cut the balloon down and send it to water assets that were waiting for us in Long Island Sound. That did not happen. It went all the way to Long Island. And so, so what we found later was that when you do an all-nighter with engineering hardware, things are just bound to not go right. So we had a connector that was supposed to connect to the cut-down mechanism of the balloon. When the balloon left Larry's hands, the connector inside separated, and so there was no way to cut the balloon down. Lucky that happened, because we did not shield the electronics inside the balloon from RF interference, because we were broadcasting with a radio. And what was happening was that the balloon was trying to cut itself at the same rate that it was transmitting a signal to the ground every single minute. And it was actually accidentally activating all the relays. And so if that connection hadn't separated, our balloon would have landed probably in the golf course 1 minute after the launch. So that's, who knew, you know? So this is our boat leaving Stratford and promptly turning around because we weren't going to land it there. So that started a nail biter of a trip where we were literally watching this thing go from the 30,000 foot mark that we were hoping for it to come down, and it went up to about 84,000 4,000 feet.
The video is so wicked.
It's crazy. It's crazy. Yeah, and then the recovery was actually pretty exciting because of the ground tracking equipment that we had at the museum, we were able to track this balloon all the way to the ground. And where it landed, it was actually here in the Hamptons. Really exciting. And no sooner had we seen the balloon drop, we went on Google Earth. We found the nearest asset that could probably help us, a golf course, a very fine golf course. And so we called them up. And while we were talking to the golf club, they were a little concerned about who we were until these golfers ran in and said, "Oh my God, there's this thing that fell from the sky." And then we were like, "Oh yeah, that's it. That's our thing. Go get it." And they couldn't get it because it was actually in the water. And so we were like, "Oh my gosh, what can we do now?" Well, luckily, it turned out that when we knew where it had landed, or pretty much where it landed, we were able to actually call up the nearest yacht club. And this boat went actually out there to pick it up for us because we were able to call him up. And so here's that dude right there. Yeah, he was a little toasty when when they picked up our bird. But I gotta love the boat's name was Slip Away. So I kept my job. It was great. It was a little dicey because we had to call the FAA and say we had a runaway balloon. But it was sort of our introduction. This has been an incredible starting point for us because we went from like not knowing anything about high altitude ballooning and trying to really push the technology in a way that would take us to some really cool next steps. Some of the next steps has allowed us to actually partner with the University of Bridgeport to actually do high altitude ballooning on real NASA flights. So these are actually NASA flights. Their high altitude balloons go up to about 120,000 feet in altitude. And so we were actually able to build a number of payloads at the Discovery Museum with university students working alongside our volunteer engineers to actually launch some of this equipment. So one of the payloads that we were going to launch on this balloon was a Servo Testbed. So we had this crazy idea. And the idea that we had in the back of our mind required us to be able to use servos, and these servos had to function in the environment of a high altitude balloon, minus 52 degrees, near vacuum. And so what we were going to do is we were going to create like a little test bed to actually mount all of these different servo motors and then put them into this container and box, and then have all the telemetry from those servo motors and the performance of those servo motors sent back down to the ground so that we can understand a little bit about how these servo motors performed in this environment. This was actually a project that was funded by NASA, and then the box itself was actually built in the Discovery Museum with the help of our university students. And so University of Bridgeport was able to get the grant money for this particular test, and Larry and a couple of other engineers at the Discovery Museum, along with the students, helped to build this platform. And so we were able to put this capsule and mount it onto the gondola of a real NASA high-altitude balloon mission. And so you can see right there, this is our box with a shameless plug for the Discovery Museum right on there. And we were actually able to control this from Bridgeport, even though it was in Texas during its flight. And here is the gondola just about ready for launch. You can see all the other instruments that are on there and our University of Bridgeport package. And here is our team at the University of Bridgeport. And we literally had a giant screen with mission control, text messaging commands to the ground teams in Texas, and they would transmit it to the balloon, and the balloon would transmit back whether or not it had executed any command. So we were doing all of this in Bridgeport while the balloon was about 120,000 feet over the southwest. And so you can see right here, here's our flight, and this is what it looks like when it lands. It landed It's pretty rough. One of the things that's cool about these landings is that they're supposed to land in places where they're remote, and so they've got this giant truck that goes out to pick up the gondola. But the truck driver actually carries with him a briefcase with, I think, like $40,000 in cash, non-sequential bills. So if it lands on something like a cow or a house, they just give the money to the homeowner and say, "We were never here." And so their NASA dollars are being used to bribe farmers in this country.
How fast does this hit the ground?
Yeah, what's that?
How fast does this hit the ground?
That's a good question. I mean,
Looks like it hit pretty good.
we were worried about it wrecking everything on the.
It just comes down at terminal velocity?
No. It's got a parachute. So it's and we're looking at probably. I mean, collision like this, we're probably looking at
So they
maybe
quick
like
10,
stuff
15,
the
40.
cow underneath it.
What's that?
So they quick stuff the cow underneath it.
Exactly, yeah.
So they can get
That's
How about, and yours came down at what? Like the same, like 10, 15 miles per hour?
our
Yeah.
balloon, our
Yeah.
small balloon.
Yeah.
No, well, so learning experiences as they are, our balloon parachute was actually slightly smaller than we should have had, and so the balloon burst. It kind of wrapped up a little bit of the parachute, so we were coming down, I think, like around 60 to 70 miles an hour.
It
So
started that
yeah.
way.
What's that?
It started that way at high altitude.
Yep, and then it starts to slow down. Once we saw that the speeds were slowing down, that's when we knew, okay, parachutes, working. So it was a little nerve-wracking, and we've got the video footage. You can see it, the balloon popping, and this thing just comes down like a rock. It's kind of scary. Had a number of different team members that were involved in this project. I also had a chance to go down for a solar eclipse mission. This particular mission was to actually image the solar eclipse from a high-altitude balloon platform. We were interested in being a part of this so that we could actually learn a little bit about doing video work on a balloon and how to actually get live video from the balloon. So we worked with a team of scientists and engineers from the University of Bridgeport. There was another team from Hartford as well. And we were under the Montana Space Grant. There were about 50 different university teams that were out all along the Eclipse track. And their job was to try and capture live video, pop that onto the internet, and then transmit it onto a website that you can actually go and check out the pictures. And so that was our job. Here's what the ground station kind of looked like. And they were all kind of turnkey kits. The payloads themselves were turnkey as well. And this is a picture of our team members. These are all team members that went down to Kentucky, myself included. So what we found was that none of that hardware worked at all. None of that. So it was only until after we did sort of the post-mortem that we discovered that there were a lot of technical issues that hadn't really been solved. And because they locked every one of the 50 teams into a single type of payload and a configuration for the payload, there wasn't a lot of room for us to be able to negotiate. It looked great when it was in the lab, but when it was actually on a balloon, it didn't quite work as well as we thought. So those were things that we kind of took in terms of a learning experience. And so,
Can we just blame Larry?
what's that? Yeah, exactly. Yeah. And then the other thing was the cut-down mechanism. So the way that NASA wanted to be able to cut down any one of the balloons at any time they wanted. And so the way that they did this was something straight out of a Rube Goldberg kind of a contraption. So the way they did this was they actually had an iridium phone in the cut-down system, and a text message would be sent to your iridium phone. It would find you, and then it would start a chain reaction where it would actually turn this guillotine really fast and cut through the tether part of the balloon and then cut your system down. The weak point of the entire thing was that the tether up to the cut-down mechanism and the tether above the cut-down mechanism, that was Kevlar, but the guillotine couldn't cut through the Kevlar. So they had this really weak cabling that was holding everything together. And what was happening was that we realized this when they designed this, but and we weren't the only team that this happened to, that when we let the balloon go, that little tiny cable snapped, balloon went, and here we are holding thousands of dollars worth of equipment. And so we were like, thank you, NASA. And so we ended up having to run around like firemen, get another helium tank, get another balloon, and then, screw the cut down mechanism and connect everything together and launch it.
How was your timing? So you're doing this way before the eclipse.
Yeah.
How soon before?
So we were supposed to go up like about 1,000 feet per minute.
Yeah.
So we were thinking about maybe about an hour before totality. Now our team had a little trouble with that cut down, and so when we lost our first balloon, it just took our entire time schedule and wrecked everything. And the other thing was that we were still kind of novices at this whole. We had never launched a balloon this big before. This was a big balloon. We did the Discovery 1. That was a cool project. We did another Trumbull balloon that we launched it and landed in Trumbull in a tree that we cut down that you don't need to hear about, but that just happened. But this was a fairly large balloon, and so we really didn't have a lot of experience with coordinating our team to do that. There was a team next to us from West Virginia. They were from Kentucky. Actually, they're from Kentucky. Those guys, they were like clockwork. They were unbelievable. They had this thing inflated. They had everything lined up, and then they had their little payload train, and they just knew how to launch this thing. So we were kind of at a little bit of a bind. And when we had that cut down mechanism and that cable snapped, like I said, we probably got up to around maybe 11,000 feet, while other teams were probably at the 30 to 40,000 foot mark. And so that was the big issue. So just learning how to do ground operations with a balloon that big, that was something that we got to kind of practice.
Did anybody have success with this?
I think there was like one. The big issue was that the transmitting part of the live video didn't quite work as well because they didn't have a big enough dish, they didn't have enough bandwidth. There were a number of technical issues that I'm not an expert on to be able to kind of explain, but when we had the system there, one of our advisors saw the whole system and said, well, that's not going to work. And we're like looking at it in Kentucky and going, well, that's not what we need to hear now.
Thanks, buddy.
But we learned a lot, and we know that 2024 is coming. And so, we're probably thinking of doing another different kind of approach. But we think we've got cut downs a little bit better than what these guys had designed. So all of this, learning how to do remote operations of hardware on a payload, learning how to do video from high altitude, all of this really kind of prepared us to what really we're excited about, and that's this. This is the HAM project. So I kind of touched upon it a while ago, and HAM stands for High Altitude Monkey, and so the concept is that we were going to launch a robot monkey on this balloon.
That's one of the symbol.
Oh, it's I've got video. It's even better. It's cool. Okay. So it was a collaboration between the University of Bridgeport, Harvard, and Wesleyan University. And what they did was that it's called a USIP, Undergraduate Student Instrument Package, and they submitted a proposal to the Connecticut Space Grant, and their proposal was that they were going to build, with the help of the Discovery Museum and our engineers, a payload that would have an animatronic, a monkey on board, that we would get live video footage, and we would be able to remotely control the monkey from the ground, and turn it into our own personal high altitude monkey. And so the inspiration for this was an actual monkey named Ham. Ham in the 1960s was launched to understand the physiology of space travel, a little bit of understanding of how space travel might actually affect humans. And so the nearest species to us that might be able to give us some more insight about space travel were chimpanzees. And so they started with smaller monkeys, but Ham was the chimpanzee that went up into space.
Did not end well for him.
Yeah, what's that?
Did not end well for him.
Yeah.
I
So
thought he was fine. What happened to him?
No, Ham was okay. All the Alberts died.
Yeah, the Alberts were like little Reese's monkeys.
yeah. He survived.
He did? Okay.
Yeah, he did survive. Yeah. The other one, I think there was Miss Baker came back really pissed off, and you could never touch her because she was like,
Can't trust you.
Yeah, I know. Can't trust people. Big surprise. Exactly. Yeah.
Laika didn't make it.
Yeah, I know.
Yeah,
I
all
did,
the
find, I
dogs
did
and
find out
the
that there was actually a cat that went into space. The French did launch one cat, and so they finally are going to make a monument, a little statue for this cat in space.
chef.
Not for Laika.
No, it was after Laika. Yeah, Laika was the first animal, and then the
First
French.
animal in orbit. There were animals in space before like that.
No, there were. Really?
Yeah.
Oh,
Yeah, lots launched on V2s and
Uh-huh.
other ones, which were just Soviet copies of the V2.
Mm-hmm.
The U.S. had quite a substantial suborbital research program in the 50s that people never talk about.
I think part of it was like, I guess it was going top secret for a while.
No, a fair amount about it was publicized, actually. They had basically refurbished V2s. They put like little monkeys on,
Yeah,
all sorts
yeah,
of
yeah.
scientific payloads. It's really cool. The Russians figured out how to copy the V2 out of their own factories, and they did the same thing called the R1.
The R1.
Yeah, and they did a lot with that. And they put small logs, I think, on like an R5 or something, right? For
Yeah, I think my favorite quote was when Yuri Gagarin said that he didn't know whether he was the first man or the last dog. The Connecticut spacecraft funding allowed us to actually work with these universities to be able to put together this package that would be sort of a platform using our mission control and ground station operations to create sort of a ham mission for students. Aspects of the mission was that it was going to be a high altitude balloon mission. We wanted to make it real, and it was designed to inspire wonder, ignite creativity. We were going to use the museum ground station as mission control. So this was sort of the idea that we would develop the hardware and then back into the software needed at ground station to be able to turn the ground control at the museum into a real ground control that managed the mission for this high altitude balloon monkey mission. We were going to have an animatronic friend on the mission inside the capsule, and this was the real challenging part, was to get live video and telemetry from the payload. Live video and telemetry from the payload. So there were a couple of ideas for the animatronic monkey that required us to be able to use these servos. And so that's one of the reasons why we sent those servos up on that high altitude balloon mission. We wanted to kind of test their performance and see how they behaved at minus 52 degrees. The capsule that was on that test mission was lined with nichrome wire and some panels that reflected that energy into the capsule. So we were literally able to control the temperature in the capsule, because one of the things that we found was that we couldn't get the capsule cold during the day. So just radiant heating on the capsule during the daytime was enough to keep the electronics inside fairly warm. We couldn't get it really, really cold. And so at night, what we did was that we waited, because the mission actually goes overnight, and then we were actually able to send signals to the radiant heaters on board the capsule and actually bring down the temperature in a very controlled fashion so that we can see how the servos were operating as the temperature got colder and colder and colder. So that was one of the things that we did with that mission, because we were thinking of using those servos in the animatronic monkey. We were playing around with different kinds of spacesuits and spacesuit designs, and our advisor, Dr. J.D. Pallas, knew Dr. David Newman, and she's out of MIT, and she was coming up with some different designs for spacesuits. And so we wanted to kind of model the spacesuit that Ham would wear after some of the spacesuits that were in development and concepts out at MIT with Dr. David Newman. And then we had a couple of different capsule designs. It went through a lot of different iterations, but we had originally thought of like kind of an I Dream of Jeannie type capsule, like a little Mercury capsule, something like that. So there were a number of different designs. One of the things that we were having trouble with was just trying to keep the weight down. We have FAA regulations that require us to keep our packages down to 12 pounds total, 6 pounds per small package. So 6 pounds was a huge cutoff for us, and that was a limit to be able to pack everything, electronics, monkey, robot, camera, all that stuff into a box that was 6 pounds. So that was difficult. That was really a challenge to get everything down to that weight. We ended up putting it into 2 packages, One was the capsule with the monkey and the video, and the other was sort of a housekeeping package that did telemetry, had the GPS, had the cut down, and the connection between the two packages was actually by Bluetooth. So we actually had two Bluetooth transmitters, and the connection between the two packages was pretty seamless. We were really impressed and surprised by that. And so we actually built a prototype, and this prototype was to test things like remote telemetry, remote robotics, and live video. And so our monkey looks like that. There he is. That's it. That's our robot monkey. So he was 3D printed, and then they had some lady at the University of Bridgeport who just does little doll costumes, and so she was kind of recruited to make the spacesuit for our little robot monkey. The monkey is mounted in the capsule, and there's an Arduino that actually controls all the different servos. When we came up with this concept, we thought that to control the monkey, we would basically use a computer interface, maybe pull down menus, any number of different things. The monkey would have different gestures, and these gestures could be seen on video live while the monkey was in flight. Our engineer, Larry, came up with an idea that actually was really kind of compelling. He thought that at mission control, you kind of need something with buttons. And so what he did was that he actually fabricated a control system for the monkey and for all the operations of the flight. And this was really kind of exciting. So this allowed me to be able to push a button, and it would actually do different gestures. Yes and no, nod his head, give me a thumbs up, all that kind of stuff. It actually would allow me to turn on and off the video transmitter remotely on the bird. It would actually be able to do things like tell me a little bit about the conditions on the bird. And one of the things that was really remarkable was that the command processor allowed me to do a cut down in a very cool way. And so the way that Larry designed the cut down is he's got like there's a little red button on the side. It has those little flip covers, kind of like a missile.
The shiny
Oh, it was so cool. Yeah, you open up the cap, then you click the button, and that didn't cut it down yet. A voice would be on the box saying that the cut down has now been activated. To confirm cut down, you had to touch and push the blinking white button, and that would activate the cut down. So it was like, oh my God, this is like badass. It was just incredible. And then one of the things that was happening was that the monkey needed sort of like a personality. And at first we thought that it can just be like a little mime puppet that just kind of does gestures. And Larry came up with the great idea that it needed a voice. And so he was able to go on Adafruit and find a voice synthesizer. And so he programmed all of these little responses. And so it wasn't just yes or no, it was affirmative, roger, all this stuff. And you didn't know when the response was going to happen. It would be kind of like different. And then he had different responses for when it was scared, when it was happy, when he was ready. It had a little intro saying, I am so happy to be on this flight, you know, that kind of thing. So there were lots of different things that, the other thing that really he blew my mind away when he was actually able to take telemetry and make the monkey pretend to be reading an instrument panel, and real data would actually be substituted in the sentence that the monkey was transmitting, so that when the monkey is saying it's at 30,000 feet in altitude, it's using the GPS data, plugging that into its sentence, and then saying it. So it's incredible.
What kind of telemetry could it give you? I mean,
So it give me a battery voltage, two battery voltage, battery voltage for Capsule monkey, and the other battery voltage for the housekeeping capsule. It could give me internal temperature, external temperature. It can give me the altitude, and we've been kind of playing around with all these different ideas. You know, it would be incredible if we could actually create a system where it could tell us what town it's flying over.
I was just saying that too. I mean,
It's got a lot of legs. This whole idea.
Well, that's great. Good for Larry.
Yeah. So Larry's been a real godsend with this whole mission. So he literally built this entire system. So I want to see this over here. Let's see. So this is the command processor.
This is the command processor for the monkey.
There's Larry.
And here is the monkey.
You guys, the exchange
that we're
between
going to
Larry
be
and the
controlling
monkey.
by radio. And are you happy, Mr. Monkey?
That is affirmative.
That's good. You're not afraid of anything, are you?
No control. Negative.
Good. What do you give us a thumbs up?
I feel great. It's the thumbs up day.
Okay. Why don't you scan the instrument panel and tell us what the
Let me
altitude
read
is?
the instrument panel. The altimeter reads 23,650 feet. Lead day battery voltage is 7.80 volts. And the monthly battery voltage is 15.80 volts.
Very good, very good. So how do you feel?
Very good. I'm feeling good. There's nothing like a high altitude balloon ride to lift your spirits.
All right. Very, very well. Give us a nice chest pound.
Say, who is the best robotic monkey around? It is H-A-M-M-E.
Wave to your...
Yeah, so it gave the monkey a really cool personality. Here's Larry right here. You can see we cut a porthole. We had thought about maybe like some kind of a video switching with two cameras, external camera, internal camera, but we were so tight on time that we thought, let's just point the camera and make a porthole, and the money shot is looking at the monkey. You can see the window, and out in the window is the ground. And so that was sort of the configuration that we ended up with. It was hard to get it down to six pounds, and so we ended up tearing apart a lot of the inside. We still had to get it down to 6 pounds, and so if you were able to see the real monkey, if you opened up its t-shirt and its spacesuit, you're going to see that we gave it a lobotomy. And it's like also we carved it up, tried to pull as much plastic out of it as we can, so trying to get it down to that target weight. Over here, you can see what the video looks like, and there was we had a video overlay that gave us battery voltage, call sign, as well as mission elapsed time. This is sort of our ground setup, and he built a second box, and that second box was to take the telemetry from the bird and actually display it on a screen, mission control style. And so we had live video footage, we had telemetry, and then we had tracking, and then our bird was actually being tracked by our ground station. So we put it all together, and actually November 3rd we launched it. And it was really kind of exciting. So I want to show you a quick video, and when you're looking at the video, just keep an eye out for the porthole, and you'll probably hear us like just screaming and yelling because we were like just so excited, you know. So here is our ground station. We got some video footage of the telemetry screen. Here is APRS. We were transmitting APRS signal to do tracking, and here we go. This is right under
launch control. This is ground control. Monkey is operational. I'm getting video footage.
That's my best NASA voice
in the porthole. Over. We have altitude 2,000 feet. Over.
That's a pretty good video outside the window there. Yeah.
Hello everyone who's watching me now. I feel like a big hero way up in the sky.
So I'm sending a command, it's executing it, giving me the gesture, and I'm seeing it live on the screen.
Transmitter up a little higher.
Well, why does it get noisy here?
Don't know. We had a little amp
Control. We're looking pretty good. I can see video footage.
on the coax.
Comes in and out a little bit, but still locked on. I'm getting telemetry, and the monkey is responding. I'm showing altitude at 3,600 feet and climbing.
Wow, he just sent him the way up to where he's going.
Let me read the instrument panel.
Stand by. He is scanning his instrument now.
The altimeter reads 4869 feet. Lead battery voltage is 8.09 volts. And the monthly battery voltage is 12.90 volts.
actually
Okay,
real
so the
data.
command was sent and is receiving the telemetry and transmitting it.
Vertical speed is
Is
10.
anybody making a movie of you?
I've got Gary here making a movie, vertical speed, looks like about 5 miles an hour.
Thank you.
APRS is tracking, APRS is tracking. We are now at 4,800 feet.
Can we get rid of that?
How's the video work?
Get rid of the square so I can take a picture.
Video is a little choppy, but we're doing good.
The antenna tracking the bird, in other words, the RS.
So it was really exciting to see all of these parts working. Video was a little choppy. We still haven't figured out quite why. I don't know, but the video that we did get, we were able to get at least,
Could have been a loose connection.
yeah, I don't know, yeah.
Did you keep video through the whole flight?
Yeah, practically the whole flight. We started losing video once we started getting closer and closer to the ground. And so what ended up happening was that we launched, this is our launch site here in Bridgeport, and X Park Avenue here. We start getting a telemetry, went right over Beardsley Park, and then what happened is that as it got to around here, just around the Housatonic River, we sent a command to the balloon. It's a command called maximum altitude. It's a command that actually sets on the bird a maximum altitude, and once it achieves that maximum altitude, it's supposed to cut itself down. Problem was, and this happened in 2 of our flights, that when we sent the maximum altitude command, the computer interpreted that as an abort and aborted the mission.
Right away.
Right away. Yeah, and so we're like, so all of a sudden now we have this uncontrolled bird, it's flying down again, and it ended up going over the Housatonic River right next to us. Of course, you know, so this parachute coming down. Cut down worked, it just didn't work when it was supposed to, and where it landed was actually in Milford, like Silver Sands. Wow. And so we were like, oh, at the edge of our seats, like, oh my God, what the hell's going to happen? And we thought we were going to lose this bird in the water. Well, it did land in the water, but it landed in this one sandbar on the beach. We planned this, of course. You know, this is how we do this. So somebody actually had to go out there in the water, roll up their pants, and jump in and get the 2 birds.
They got their feet wet.
And they got their feet wet, exactly, yeah. So we did, it was only until much later that we discovered, and Larry could probably explain why the software did that, but the best way that I can describe it is that when we entered a number for maximum altitude, the way that the computer program interpreted that number, it's either a floating point or something like that, it added a negative sign to it.
Overflow the integer.
Yeah, and so when it did that, the number was too big, the floating point integer, and then the extra bit flipped, and the computer interpreted that as a negative number. So when we put in, cut it off at 30,000 feet. Oh, negative 30,000 feet. Oh, I'm above that. Cut. You know, that's what happened. It won't happen again. So yeah, so we're excited.
We are next flight.
Next flight's March. Yeah, so we're
What's the goal of it this time? How high are you going to go?
Higher. We want to try for 30,000 feet. So that's sort of our kind of target for this particular mission. And so if we can get to around 30,000, maybe do a max altitude. We're a little still nervous about that, but get it up high enough so that we can actually see how far the video can work. So, you may be right, there may be some connection in that whole system that we need to kind of take a look at. There's a lot of jostling, and so I wouldn't be surprised. I'll take a look at that to see if as the payload is moving or jostling around, there may be some loose cabling or some cabling that we used a REN cam, which is a kind of camera that's used for remote controlled airplanes, that kind of thing. So it's a lot of parts that were kind of put together. It's not a streamlined package or a product, but it's something that we hope can be compelling enough that in the future we can probably build these systems and then use them as a way to teach kids about space exploration by actually giving them a friend. And so that's the idea. This is sort of like an educational program.
I'm surprised your porthole looked as good as it did. You really could see. I mean, I saw the water out a bunch of times. I saw the
Yeah.
sound. I saw buildings, and
Yeah, that was the money shot I was looking for. Because for me, they were like, everybody was kind of telling me, why don't you just put the monkey in a green screen or something like that, and just kind of. And I was like, no, it's got to be real, you know. And then they're being engineers, like, well, if we lose the monkey, that's okay. And I'm like, no, once kids fall in love with this monkey, you got to get the monkey back.
can you get a camera on the outside too of the box? Or is it just
We
weighted?
did have a GoPro, and so we did get some GoPro footage. We've kind of come to the point where anytime we're doing ballooning, the GoPro is just part of the package. And so, we get some really good footage that we can get after the mission to be able to kind of, document all the different parts of the mission. So that's what we've been working. We've got a couple of teams that are working on this, and we've got a few other projects that we're playing with. We've got, and Dave can tell you a little bit about one of the projects. We're thinking about light APRS, and basically the gist is that we've got these, they are an APRS system on a chip, and it's a board that has the GPS, the radio, all this stuff, and we've been able to get the package down to the size of a styrofoam box that you can put a teacup in, so it's like really, really small. And so with APRS, you can track it all the way to the coastline, and then once it gets into the ocean, you can't track it anymore. But they just came up with a version that you can actually use Whisper and 2 meter, I think it is.
Yeah, it's got HF on it, so you can transmit on, say, 20-meter amateur band and transmit its own.
Yeah. And so the idea is that we can actually use it to actually track it while it's in flight across the Atlantic. And so we've been playing with this idea of like maybe doing like a race where each high school will build one, and then we have a big launch party, and then we just see which high school makes it to Europe, that kind of thing. And then track the entire thing. Yeah.
I seem to remember the Hamptons mission. There was at HighAltitude. There was a lot of spinning.
There was, yeah.
So how did you stop that on the monkey mission? Like
Oh,
gyroscope or something?
Yeah.
This is quite low. I saw it spinning. I mean, it was definitely spinning.
Yeah.
Nothing like that.
No, nothing like that either. Yeah. That's when it was coming down, though, wasn't it?
We had a bit of a trick. It was a little bit more tough. I mean, when the way that we kind of put the I guess the tethers on the thing, we didn't have it like on a single point. I think we kind of had it coming up a little bit. I don't know.
The first launch had a lot of wind too.
Yeah.
So one reason with the first launch we wanted to cut it out early was because of the wind. I recall it was going like 70 miles an hour horizontally with some of that wind. Greatly attributes to
This was doing 10 miles an hour.
Yeah. I mean, we were kind of lucky with the weather. This was probably the last day that we could probably have done this launch in that year.
Wait, was the monkey talking all the way to the end?
Yes. Yeah. I didn't have the video was the toughest part, trying to maintain the video on the monkey. But we were still getting telemetry. I was still sending commands. The monkey was executing all the commands, and so we think we've gotten to the point where we understand how to send commands and receive telemetry with our radios, and the radios track, and so the antennas are always tracking the entire bird the entire time.
So did you know immediately that it landed on some kind of
No.
whole sidebar?
Yeah,
sandbar?
we did not. No. So what happened was that we had Dave was out there with the ground crew, and we had told them where we thought the bird was going to land based on our weather predictions and our
Top of a Black Hawk.
Yeah, exactly. Yeah, exactly. Yeah. And so when we told them that we had a premature abort, that we had them on the phone, and then they turned around and they were able to track on their IPRS. They were able to see it as well. But once they got a visual of it, that's when they called us and said it's on a sandbar.
But you couldn't tell from the video that it wasn't floating.
We couldn't, because once it's on the ground, the antennas are in the water.
Yeah, it landed in salt water.
Yeah, we couldn't see
Not
it.
gonna work.
We actually knew before you guys called us.
Oh yeah.
Yeah, because we were traveling out to I think it was going to be like towards New London.
Yes.
Where it was
Yeah.
originally going to land. So we're on 95 heading out that way, and I've got the APRS in the car. We're watching the altitude, and then we see a transmission going. Wait, wasn't that number lower than?
Yeah, exactly. Yeah.
And then it did it again. okay, let's get off and
Yeah,
turn
right.
around. Something's going on.
Yeah. And so the APRS system has been a godsend in terms of tracking. Some people have been using like Spot to kind of find their balloons, but with the system that we've been able to put together and just adding the APRS on top of that, I mean, we literally have been able to track these things down to their landing point, practically down to their landing point. So that's really good when you want to really recover the hardware, for us at least. And we're able to at least be able to tell, our ground assets and recovery teams, that where they can actually start to find this. So we've got another high school team that I'm working with on a couple of high altitude balloon missions, and so we're putting together another package, but we're looking at launching the Monkey again, a little more media and a little more social media around it as well, probably around the middle of March, maybe March, I think like 14th or 15th that weekend, and a backup date like the March 22nd. But the hardware survived. We've been able to test it. We've played around with it, and it still works. And so we're thinking of trying another flight. NASA was really interested in figuring out whether we could do this, and one of the requirements was that we had to give them a video of the actual flight. So they looked for like 7 minutes of video. That was like the big thing that we were all nervous about. So somebody had to Gary was basically with his iPhone documenting, this whole that movie, and that was the money shot, the command, the monkey responding, the gestures, and everything was all happening live in flight. So we want to really kind of push the monkey and see how far hand can go. And that's our next step to kind of push it a little bit.
That's a home run, dude.
What's that?
That's a home run, man.
Yeah, it's really
That's great.
Yeah. Yeah.
Where did the high school teams come from? Is it a science class or a club?
Yeah, so it's been kind of like hit or miss. So so I've been kind of on the down low on that. So I've been working with Fairchild, mostly Fairchild Wheeler, but and then I've actually had one kid from St. Joseph, and so I did presentations about. We have a rocketry club at the museum, the high-powered rocketry. And I think I did a presentation here on the high-powered rocketry projects. So right now I've got a civil air group that I'm giving them like carte blanche. They're like a couple $1,000s to build like a 6-foot rocket. I've got University of Bridgeport putting together an electronic payload to go in the rocket, and then I've got the high altitude balloon team as well. So I've got a lot of different irons that are kind of in the fire. But a lot of that funding came from NASA. So the ballooning that I'm working on, the high altitude ballooning, the rocketry, but the NASA grant kind of ends this year, so I'm in a mad dash to try and spend as much money as I can on that.
The reason I ask is because my son's high school has an avionics class.
Oh, wow.
Which I have social studies, so we didn't have avionics.
Yeah, I know, exactly.
So I didn't know if it was that type
I
of
had
thing.
morality, Yeah, no, I mean, if they want to stop by and kind of do some, meeting of the minds or something like that, I might be able to, we could probably, talk or something. Yeah, definitely. I mean, I'm trying to come up with ways to spend as much money as I can. I've got about
We can help you with that.
Yeah, I know.
Yeah, fall the grenade for you, dude.
Yeah, exactly. Yeah. So there's a system that we're really interested in getting. It's called a GRAW radiosonde kit, and basically it's a turnkey weather balloon system. And all you just need is to buy the balloons. The payloads themselves are about like $250 to $300 a piece, but the ground station is like $12,000. So I've got about we've got it close to around $18,000. So I was thinking of like really, getting this system, and then what we can do is we can go on site to a school, and then we can then do radio sondes or weather balloons, and all that telemetry is coming to the ground on a screen on a laptop, and it's basically the whole kit is there: antenna, ground station, software, all that stuff. What we're trying to do is we're working with the company because we want to get the data not on a single screen, but we want to separate the data to workstations. So if you can do that,
Each kid can monitor or something.
exactly, yeah. So what the key thing, and this is sort of the step that's still kind of eluding me, is I've got the hardware that's in the extreme environment. I've got the ground station with all the computers. It's the middle piece. How do I take that data and then separate it out into the workstation so we can do this kind of work mission control stuff? that's our piece of it. But so definitely if you wanted to have it come to the museum or sometime I could show them some of the hardware, some of the things, and even at the very least, we can buy an APRS system, and then we can just see how far it goes with our tracking. So you can buy balloons that don't pop, so we can see how far it goes.
Do you guys have a secondary tracking station? I mean, I'd like us to do that.
You are.
We are.
Yeah, no,
The APRS right there.
yeah.
This is our second. Okay.
Yeah. It with just the rotators and UHF and VHF and whatever software we have, we've got like this software that we developed called BaseApp, and BaseApp is designed to talk to the hardware and control the antennas. Wow. So that's what we've been kind of working with.
Yeah, I want to have something so we can communicate with the ISS.
And that's our big thing. That we're taking these steps because the real holy grail of the whole thing
is the ISS.
Is the satellite. It's space. Yeah. And so that's why we're like working like mad at the museum to put together the package for the disco sat, the satellite.
Yep.
And so it's all the steps to ballooning to the satellite. So that's
how far away? We haven't talked about the disco set at all today. How far away?
It's slow. So I think the big part is we're working with a company. And what's happening is that they've had a change in management, and at first you can buy parts, but now what they're trying to do is they try to sell you a system. And so they've got some of the best parts for CubeSats around. The problem is that they want to sell it to you all as one piece and hand you a fully functional satellite, and add all the non-recurring engineering costs on top of that.
Right.
So it would take $100,000 worth of parts and quadruple it. So that's the art. That's right now we're talking to this company to kind of, hey, listen, just give us the damn parts.
Yeah.
Because we have the launch initiative already. If we can build it, then we can launch it. That's the key right there.
Cool. Thanks, Dave.
Yeah.
Well, thank you.